Okay. So Yier will tell us more about KPZ and its short time Layers deviations.
So I can start?
Yes.
Okay. First, I want to thank Ivan and also Evgeny for the nice organization of this event. And today I'm going to talk about the short time large deviations of the KPZ equation. So this is a joint work with Li-Cheng and Tsai from Rogers. So let's recall what is the KPZ equation. So it's a nonlinear stochastic PD given by the following form, with C to be the Gaussian spacetime white noise. So you can think of this H as the height function of some growing interface in your environment, where T represents the time variable and X represents the space variable. Okay, so X is one-dimensional, and as mentioned before, the solution theory of the KPZ equation is not well posed in the classical sense because the spacetime white noise is something very rough, and because you have a nonlinearity at here. So one way to make sense of the solution theory is to look at a different stochastic PD called the stochastic heat equation. This form is given by here. And it's a linear equation. So the solution theory of which is well posed, which means the solution exists and is unique. And so the relation of the KPZ equation and the stochastic heat equation can be seen as the following. So if you assume everything is smooth enough, so you assume the noise is very smooth, and you take the exponential transform of this H, and then apply the formal computation about the partial derivative using this chain rule on the exponential, and also use the relation of the KPZ equation, you'll see formally this exponential of H will satisfy the stochastic heat equation. So one way to define the solution theory of the KPZ equation is just we take the solution of the stochastic heat equation and we apply the logarithm to it. So this notion of the solution is called the half-curl solution. And actually it indeed makes sense because we have the positivity of stochastic heat equation. So this C is always something positive, so you can take the logarithm. And in this talk, we'll also restrict ourselves in one type of very important initial data for the KPZ equation, which corresponds to a narrow wedge. So this initial data, as you've seen before, is not directly defined for the KPZ equation, but really for the stochastic heat equation, and you started from a Dirac mass from 0. Okay, so this is basically our setup. And okay, so let me just repeat a little bit, as in Sean's talk. So thinking of the solution of your KPZ equation as the height function of some growing interface, so a natural question to ask is how does this surface grow? So the speed and the fluctuation. So actually in the work of Amir, Crow, and Costel, where they show the long time asymptotic of the KPZ equation is given by this tracy with GUE, something from the random matrix theory, at the beginning. And on the other hand, so in this talk, actually, we're going to focus on the short time behavior of the KPZ equation. And actually, in the same work, they also show that if you let time goes to 0, then the fluctuation of the KPZ equation is given by a Gaussian random variable. Okay? So this is kind of the fluctuation limit theorem for the KPZ equation, in the short time regime. So having the fluctuation limit theorem, a natural question to ask is how about the large deviation, which corresponds to we look at the probability of H to deviate from its typical value in a large size. And actually, there's a deeper reason why we want to understand this large deviation for KPZ equation when time goes to 0. It corresponds to we want to understand when time is really small. If we look at this lower tail probability of the KPZ equation, how does it decay in terms of S? Okay, so think T as something very, very small. And so naive guess is, okay, we have the fluctuation limit theorem. So this decay might be just as in the fluctuation limit, where it's Gaussian decay. So we should have quadratic law. Actually, in a physics work, by Kolokolov and Korshunov, where they predict, actually it's not the case. And in fact, when you take S to be very big, their prediction is you'll see the 5½ power law which corresponds, so S is very big, corresponds to deep lower tail. So you will not see quadratic power, but instead this 5 half power. And actually, this 5 half power law was proved rigorously in the case for KPZ equations starting from narrow wedge, where you take time to be very big. And so either take t to some finite big number or take t to infinity, so in the large deviation regime. Actually, that was established like in the work of Ivan and Promet, and also like by Li-Cheng and Katzav clients. So what we did like in this work is, as we mentioned before, like we want to first establish a large deviation of the KPZ equation in the short time regime. And after that, we want to look at like the rate function, the lower tail rate function, to see if we indeed see this 5 half power law as we probe very deep in the lower tail, so as predicted by this physics book. All right. So yeah, so this is our result. So we established the first like rigorous large deviation principle for KPZ equation in the short time regime, which corresponds to look at the probability of the following event, which corresponds to h plus, so this corresponds to typical value, either bigger than some positive number, positive fixed number, or smaller than some negative fixed number. So this corresponds upper tail or lower tail. And our large deviation really tells you this probability will decay exponentially with speed given by 1 over root t at here. And the rate function corresponds to this 5 plus or 5 minus, depending on whether you're looking at the upper tail or the lower tail. And these rate functions, they can be expressed in terms of a variational form. And more importantly, what we show is if you look at the asymptotic for this rate function, in particular for the lower tail, you will see when s approach to 0, the rate function behave asymptotically as 1 over root 2 pi s squared. It's a quadratic power law. On the other hand, if you let s goes to infinity, indeed you'll see something like this 5 half power law, like appears in the previous slide, like as in the prediction, and you'll get the constant to be 4 over 15 pi in the limit. So this quadratic power law, when you look at s close to 0, like in other words, you look at the tail behavior for your KPZ equation near the center, actually, it's not very surprising you'll see this, because this really corresponds to the regime of your fluctuation limit theorem when time goes to 0, because this 1 over root 2 pi s squared is really the tail exponent of this Gaussian random variable in your fluctuation limit. Okay. The interesting thing is really when you go from, so look at the tail from the center, when you go deep, you'll start to go into a new regime corresponds to this 5 half power. Okay. And despite, like as we seen here, the long time behavior and the short time behavior of the KPZ equation, so in the sense of fluctuation limit, can be very different. So one is Tracy-Willem fluctuation and the other is Gaussian fluctuation. But as long as you probe very deep, like in the lower tail, you actually say the same behavior about this 5 half power law. Okay, so the long time behavior was confirmed in these results. Okay, so something like about our method. So like I don't really want to talk very much about it. So like we do not really rely on like the celebrated exact formula for the KPZ equation derived by like Meerson and Costel. And actually, this method like also works for the method of our proof also works for like other initial data, like the flat initial data. And you can also prove this 5 half power law and with a different asymptotic at here. Okay, so you might wonder what happens for the upper tail. So actually, it is conjecture. Okay, so when s goes to 0, this is also the Gaussian power law. It's also what happens for the upper tail near the center. And when you go deep, it is conjecture that you will have a 3 half power law. And we have some idea on that, and that we're still like working on it. Okay, so it's like I don't really want to go to detail in our proof. So let me just present a phenomenon that appears like in our proof. So to prove this 5 half power law, so one key aspect is really to look at last passage percolation in certain deterministic environment and to understand what is the geodesic correspondent. So we start from the origin, like inside some deterministic environment, and we want to understand the geodesic. So the geodesic, like in this last passage percolation, is basically like unique. If you start from 0 to like elsewhere, for example, you start from the origin to a position like here, you just go around this bold curve, then you go straight. But there's a non-uniqueness happen when you like look at the origin and end at the position time 2 and space 0. Actually, there will be a one parameter family of the geodesic, which forms this lens shape. And this family of geodesic is really one key aspect about proving this 5½ power law. And as a phenomenon, I just want to...
We cannot see your screen.
Sorry?
We cannot see your screen, at least me.
I'm able to see it, so.
You're able? Okay, so it's my problem, sorry.
Okay, so sorry, like you cannot see it, yeah. And so as a phenomenon, actually, this is something like reminiscent of a work by Basu Ganguly and Alan Tsai, where they look at the last passage percolation. So in general, the last passage percolation, if you look at the geodesic, so you will like localize around the diagonal. But when you do the lower tail conditioning, so something similar as we're doing the deep lower tail, so you condition the last passage time to be very small than your typical value, so much smaller than the typical value, then they show this geodesic will start to delocalize. Okay, so despite the situation, like for the case here, it's not totally the same, but the phenomenon is something similar. So it might be something interesting to think about. Okay, so that's my talk. Thank you.
Okay, thank you very much here. We do have time for questions. So anyone who has them, feel free to unmute yourself.
I should go to my page.
I think I've asked you this before here, but I forget the answer. If you look at 5+ as s goes to infinity, do you have the behavior?
Yeah. So like we do not have a proof like for now, though like we have some idea about showing that. So the conjecture is like you will see the 3½ power law. And actually the tail exponent will be like this 4/3 s to the power 3½, which like kind of coincides with the Tracy-Widom right tail, but I think it's kind of like a coincidence about this.
You think it's a coincidence, really?
I think it's more a type like the tail of the KPZ instead of the Tracy-Widom, because we know that the KPZ in the like in the long time asymptotic in the large deviation regime, you also see this like 4/3 like as to the power 3½. But it doesn't like really mean that this 4/3 as to the power 3½ it's really comes from the Tracy-Widom, because we see like in the lower tail they have something different, right?
Mm-hmm. Okay. Other comments, questions? Okay. So let me stop the recording.